All right, maybe we should start the lecture. Hi, everybody. Welcome to the 13th lecture of Differential Privacy. We were thinking of wrapping up the chapter on differentially private machine learning with some remarks on differentially private deep learning. Yeah, that didn't happen last time. Today, I'll try to actually wrap up this chapter of the course. You may see that the deadline for the midterm report is due, so please try to submit the midterm report this week. And for the homework two, for the last question on homework two, yeah, before it's ready, make sure that you start working on the first three questions, and the last question like will be ready. So I run into some time management issue last week that I didn't end up finishing like writing the code template, but it is working, and I'm just gonna have to polish everything before you guys run into all sort of issue and get back to me. Okay, so yeah, that will happen very soon. Yeah, please remember to submit the midterm report this week for your project, and for the homework, yeah, the programming assignment will be available to you. Yeah, as soon as I'm able to yeah do everything that I can about the notebook. All right, so we'll start a quick recap of the last lecture. Last time we focused on the utility of the noisy gradient descent mechanism. So this is just running gradient descent and with noise added to the gradient, and that makes the gradients stochastic gradient. And so the main tools of the analysis is the convergence, the different convergence theorem of the stochastic gradient descent algorithm under various assumptions from convex optimization. Right, so we want to assume the functions, the loss functions are convex, Lipschitz, and sometimes smooth, and sometimes strongly convex, and that gives us different convergence rate, and different assumptions translate into different privacy utility trade-offs in terms of differentially private learning with the convex ERM problem. And then towards the end, we commented on the computational complexity of the noisy gradient descent algorithm, because in every iteration, in order to update the parameter for just once, we need to go over the entire data set to calculate the individual gradients and then aggregate them before updating the parameter. So this is a bit inefficient from the modern learning perspective, because we're talking about data sets of size millions, if not billions, number of data points. And then the standard technique in machine learning, without worrying about privacy concerns, is to use the stochastic gradient descent, which randomly sample, say, a small mini batch of the data set, and then compute the gradient on that mini batch, and then move towards a negative approximate gradient direction. Right, so that's the idea that made like the gradient descent-like algorithms highly scalable to large data sets. And we were wondering whether that could be applied to the problem of private learning. And the key technique that we learned last time on how to get it to work for differentially private learning is the so-called privacy amplification by sampling, which we'll talk a little bit more about today. And the last and most important issue that we didn't address is what is a computational comparison between the noisy stochastic gradient descent versus the noisy gradient descent. Right, so the noisy gradient descent is inefficient, but how about noisy stochastic gradient descent? Is it gonna save us factors in terms of the size of the data set? What is the final computational efficiency for noisy stochastic gradient descent? Can we get away with something like a one-pass algorithm that just go over the data set for once? Right, so we'll see these considerations in today's lecture, and then we'll see how the noisy stochastic gradient descent algorithm can be applied to the deep learning setting. All right, so this is a summary slide for the privacy utility trade-off for the noisy gradient descent mechanism that we covered in the last lecture. We see that comparing to the output perturbation and objective perturbation, the noisy gradient descent algorithm is more is I guess more general, and also it gives you better privacy utility trade-off. So these are measured in terms of the normalized access risk. So it's an average of the suboptimality across the different individual data points loss function. And all these algorithms achieves epsilon delta differential privacy with the epsilon and delta parameters inside. We can see that noisy gradient descent for Lipschitz plus convex and with additional smoothness condition and with additional assumption on the form of the loss function being generalized linear. So in all three categories, noisy gradient descent achieves the same excess empirical risk. So this is in terms of the optimization problem, how much that you're able to optimize this objective function, and this is the little alpha parameter from the exponential mechanism, and we can see that the expression matches with the best possible performance of objective perturbation under the strongest possible assumption, and it is shown in Basile et al. Using arguments that are related to the packing argument, but slightly different. You need to use divergences and so on and it was shown that these rates are also information theoretically optimal. So no algorithms are able to achieve a privacy utility trade-off that's better than these numbers under this family of problems with like at least in the minimax sense, like so these lower bounds hold in general. So there exists at least one problem within this family that's hard for any algorithm that you will incur like such suboptimality. In this sense, the noisy gradient descent is really the optimal algorithm for this method information theoretically. Okay, and it is also more general because it adapts to the strong convexity. So if we choose a learning rate in the slightly different schedule, then we can achieve faster convergence as the number of data point goes to infinity. And it also comes with a straightforward analysis for the non-convex optimization. And the convergence now is measured in terms of the first order optimality condition, in the sense that whether this algorithm will return something that's sufficiently close to a stationary point, right? Which includes the local minima, local maxima, and stationary points, and so on. But in deep neural networks, all the stationary points are quite unstable, and all the local minimas are quite good. So converging to a good local minima can often mean that you're already very close to the global optimal solution. Yeah, in terms of computational complexity, so this requires us to look into the convergence guarantee of noisy gradient descent a little bit more carefully. So the typical kind of convergence guarantee of the noisy gradient descent is in terms of something that's little something that's on the order of 1 over t, or order 1 over square root of t, and then plus some factor that depends on sigma square over t. And since the sigma square over t is set to be L square over rho, so this is where rho is the concentrated differential privacy parameter that we set ahead of time. So the last term is a constant, and the last term is what we get in the previous slide as t goes to infinity. So when we make the noise level and also the number of iterations going to 0 at the same time, going to infinity at the same time. Meanwhile, when we are making the like a step size is infinitesimally small, and this algorithm converges to something called a gradient flow, where you are making a tiny little step like towards the negative gradient direction in every iteration. And in this case, you are guaranteed to converge to the information theoretically optimal solution, because the first term will go to 0, while the last term will stay as a constant as a function of the privacy requirement. Okay, but that brings us to the question of computational complexity. So how many iterations do we actually need for us to obtain the optimal rate in the ballpark of what is possible, right? So the idea is that we want to choose this t to be just large enough such that the leading term, such a term that goes to 0, matches the kind of information theoretic limit. So we got a constant factor of 2 in front. Meanwhile, that's the most computationally efficient algorithm that can give us the information theoretic limit up to a universal constant. Okay, so we've worked it out in the last lecture for the several different regimes. For the convex and Lipschitz case, we've seen that we need this number of iterations to be larger than this quantity. In the convex and smooth case, we need to be larger than, and strong for the strongly convex case, we also have the different calculations from the last lecture. So these are like more or less inspecting this convergence bound and then comparing the two terms, and then like solving for the inequality that the first term is smaller than the second term, and then you can get these expressions. And since rho, since for any rho CDP mechanism, it implies rho plus square root of 2 rho log 1 over delta approximate differential privacy. Then when rho is not too large, then rho is on the order of epsilon square. When epsilon is a like standard differential privacy e to the power of epsilon kind of multiplicative factor. And then in this regime, we can replace rho with epsilon square. Okay, so what we can see is that the number of iterations in the strong when we are not making assumption on the smoothness is proportional to n square. And when we are making smoothness assumption, then the number of iteration can be reduced to something that's proportional to n. Another remark is that these are measured in terms of the number of iterations, but every iteration actually costs us quite a bit, right? So every iteration requires n gradient oracle call. So we need to evaluate the incremental gradient oracle for every single element. So in terms of the number of so-called incremental gradient call, and then this complexity, you need to multiply this by another n. So this is n square, n cube, and this is n square epsilon, and this is also n cube epsilon square. Okay, so it's like cubic time algorithm. So they are quite bad in practice. So when we run this, like some linear time, you don't really feel it, and if it is quadratic time, then you cannot do it beyond, say, 100,000, and if it is cubic time, then yeah, so you are limited to regimes that when you have like say 10,000 data points, and beyond that, then things becomes like quite inefficient. Okay, and well, the key hammer that we use to address this computational bottleneck is a privacy amplification by sampling. So the idea is that if we sample the data set before we apply a particular randomized algorithm that satisfies a epsilon delta differential privacy, and then this sampling procedure, this randomized sampling procedure, is actually helping you with your privacy guarantees. In some sense, it amplifies the privacy guarantee by a factor that's proportional to the sampling ratio. In a good regime, at least, the actual transformation is nonlinear. But in the regime when epsilon is small, e to the power of epsilon minus epsilon is roughly proportional to epsilon, and you can use the bound of log 1 plus x being smaller than x to obtain this type of bound. Okay, so these are the kind of inequalities so log 1 plus x looks like this, and x looks like this. So x is always larger than log 1 plus x. Yeah, so the key idea is that when we do stochastic gradient descent, we want to take advantage of the random selection of the mini batch itself not just for computational efficiency, that's like the motivation of doing this sampling in the first place, but also for making it a stronger differentially private algorithm, right? So in this case, every iteration will cost you less computation, but also it costs you less privacy budget. So then this the mechanism that first subsample the data set before applying Gaussian mechanism to that randomly chosen mini batch is called a subsampled Gaussian mechanism. And from a DP perspective, this like noisy stochastic gradient algorithm like it's just a composition of T subsampled Gaussian mechanism. So we call this composition first subsample, then apply Gaussian mechanism by adding noise to release the sum of the gradient in that mini batch called subsampled Gaussian. And then the kind of analysis for this uses the Renyi differential privacy. So in a good regime, in a good regime, if a Gaussian mechanism satisfy rho 0 CDP, and then it can be shown that the subsample Gaussian mechanism, so the subsample Gaussian mechanism, it doesn't actually satisfy the concentrated differential privacy, but it has an interesting RDP bound, and that RDP bound looks like gamma square rho 0 called a truncated concentrated differential privacy, which means that there exists some threshold for which the Renyi DP parameter of this sampled mechanism with probability gamma alpha, and this is smaller than some order of gamma square rho 0. When this M is just a Gaussian mechanism satisfying rho CDP for alpha smaller than some threshold. It doesn't apply to all possible alphas seeing this CDP bound when like this is just a linear upper bound of the Renyi divergence or the Renyi DP upper bound. Like you guys still remember the connection between concentrated DP and Renyi DP, right? So concentrated DP is a linear upper bound of the Renyi DP, and the Renyi DP is a pointwise upper bound of the Renyi divergence at order alpha for when you apply this mechanism to two neighboring data sets, right? When you max over the arbitrary pair of neighboring data set, you obtain upper bound, and that's Renyi DP. And the concentrated DP implies an upper bound of the Renyi DP. And as we talked about last time, this truncated concentrated DP implies a truncated version of the Renyi DP bound. So beyond this threshold, then I don't care about how large this epsilon of alpha is. It can be infinity. But when alpha is smaller than this threshold, I want to make sure that they satisfy this linear bound. Sorry, I missed this alpha parameter. It's not bounded by constant, but rather bounded by a linear function that grows with alpha. Okay, so once we I guess once we have this, it remains for us to analyze the utility of this algorithm, and in order to do that, we need to by the way, whenever we have this Renyi DP upper bound like this, then we can compose this Renyi DP upper bound over the T iterations. So let's say we run this for T iterations, and the total NoisySGD alpha for the same alpha, this will be smaller than something that's order of T times gamma square times rho 0 times A times alpha. Right, so that will be the truncated CDP bound for the whole NoisySGD after composition, and then we can convert this into epsilon delta DP. So provided that the optimal alpha that we choose to convert this to epsilon delta DP falls into this region of a predefined threshold, then we're good. Then this is as good as this mechanism satisfy the standard standard like CDP with the same parameter. All right, so in the utility analysis, it requires us to use the same convergence theorems for the stochastic gradient descent because we are getting unbiased estimator of the gradient as well. The difference is in the parameters because now every iteration has a two sources of randomness and two sources of error in our update direction. So one part is coming from the noise that we added synthetically from this Gaussian mechanism. The other half is coming from our random sampling of the of this mini batch, right? So both of them contribute to the part of the variance of the gradient, and we actually need a scaling factor in order to make this unbiased. So let's write it down. So in NoisySGD, the gradient estimate direction at tth iteration is equal to 1 over gamma. So this scaling factor is important to offset the differences of the sampling. So recall that we are minimizing the sum of the loss functions rather than the average. And then I'm choosing everything that's coming from this mini batch, and this I is random. This I is randomly chosen from the sampling procedure. And the gradient of Li, so this is i's data point that happens to be picked by this random mini batch at this position, say theta t. And then I'm basically adding noise to this summation with parameter sigma. Okay, so that's the kind of stochastic gradient that we construct. And this rescaling factor ensures that when we take expectation of this over the random subset, then we are getting an unbiased estimator of the true gradient. And then we've worked out in the last lecture what is the variance of this operator of this gradient. So this parameter is important for the for applying the convergence theorem for stochastic gradient descent. And from the last lecture, we've seen that there are two terms that contribute to this. And the first term is a term that we synthetically added. So this is d times sigma square over gamma square. Okay, so this is obvious from this 1 over gamma multiplied with this this noise vector. And since we're adding over the different coordinates, and then hence the factor of d, the factor of dimensionality. On the other hand, like for the other half, let's say that we're getting gamma times n samples out of the data set of size n. Then we should expect that the variance would scale like the number of data points that you actually square root of the variance should scale like the proportional to the number of data points that you actually select, right? So I waved my hand last time when calculating the second part of the variance because it requires us to use Bernstein's inequality, which I didn't talk about. But yeah, please believe me that it is on the order of n times L square, where L is a Lipschitz constant or the boundedness of the gradient. So when these individual L's are bounded, and then we are also sampling each one of them with probability gamma. So the second term, the variance, is proportional to n L square over gamma. So notice that this is over gamma rather than over gamma square. And how we obtain this gamma is by first of all, there's this gamma 1 over gamma square factor, but then the variance is proportional to gamma times n, and these two got canceled out, and then we get this n L square over gamma. Okay, so there are some interesting differences in the dependence of the sampling probability to obtain this mini batch between the two terms of the variance. Okay, yeah, so now let's take a look at the nonlinearity of this amplification by sampling. So I've talked about this last time as well. There's a phase transition when alpha is small, then we get this gamma square times rho kind of amplification. So you get orders of magnitude improvement due to that you are sampling the mini batch. But when alpha is large, when we're considering like really high dimensional moments, then you do not actually have the amplification by sampling effect for those that are for those Renyi DP. So it becomes more or less the same as that of the Gaussian mechanism without subsampling. Okay, so everything should be believable because the RDP of the Gaussian mechanism should always be an upper bound, and it is a valid upper bound here. And what truncated CDP that I was talking about is that, well, we are gonna apply this linear upper bound here, something that grows with linearly with alpha with some slope, and this is always an upper bound to this quantity up to some threshold, and I guess I guess this will be the threshold. Okay, so what is that threshold will have an impact on our computational analysis of this method. Okay, so from a tight analysis, a more precise bound would say that this threshold, let's say that this is alpha star. Alpha star satisfies that alpha star times gamma times e to the power of alpha, like the Renyi DP of this base mechanism alpha star. So this is roughly 1, right? So when this happens, then this is a position for the phase transition. But this is like somewhat difficult to manipulate, right? So we can obtain slightly weaker bound, but which gives us the algorithmic tool that we can use to derive provable guarantees, and that brings us to the truncated CDP that I mentioned. So here's the theorem from the truncated CDP paper that's very handy for our purposes of analyzing this noisy stochastic gradient descent algorithm. So this says that for any mechanism that satisfy the rho CDP, so you have a Renyi DP upper bound that's linear, then the sampled version of it satisfy something like a linear upper bound as we talked about earlier, and the threshold is like proportional to 1 over this rho parameter, proportional to log 1 over sampling probability over this 4 times this rho parameter, right? So this is somewhat useful for us. It does places a constraint on how large this alpha can be, which we'll see what's the concrete impact in our analysis in the next slide. So what is this constraint? Let's try working it out from first principle. So what does this constraint has an effect on our choices of this rho parameter and on our computational computation requirements in terms of how large this number of iterations needs to be. Yeah, let's say that ultimately we want some epsilon delta DP guarantee, and we know that suppose we the overall mechanism satisfy the rho CDP, then we can choose this epsilon to be rho plus we can choose rho such that this this epsilon is satisfied, and rho is equal to 2 rho square root log 1 over delta, right? For this, if we fix delta, say delta to be 10 to the power of minus 8, and then we want to satisfy some epsilon budget, and then we want to choose this rho accordingly, and this is a kind of a result that we get, and in order and the question is that in order to get this, this is for any rho CDP mechanism, but in order to get this, we need we need to make sure that this alpha that is being used to obtain this bound is actually achievable. It's actually covered within this limit. Like suppose this is a composition of truncated CDP algorithms. Okay, so let's try working it out. So I believe this was in the second homework. But how do we get this? We can go back to the Renyi differential privacy. So So for Rényi differential privacy, we know that it satisfies epsilon delta dp with epsilon equal to a minimum of alpha, and then we have this epsilon alpha and plus log 1 over delta alpha minus 1. And if we apply this CDP upper bound here, we get alpha times rho plus log 1 over delta over alpha minus 1. And this is equal to a rho plus alpha minus 1, rho plus alpha minus 1 log 1 over delta. And what is a minimizer for alpha? How do you minimize this? You basically choose this alpha to balance these two terms, and you can take the derivative and set alpha to be zero, to set this alpha minus 1 parameter to be 0. So the optimal alpha will satisfy this alpha minus 1 is equal to log 1 over delta over rho square root. Right, so that is a choice of if we move this to the other side, that is a choice of alpha. So what we want to make sure is that this alpha star is covered under this this requirement, right? Under this requirement, and what that is saying that so this row from the previous page, so this is the row of that of the Gaussian mechanism. So let me call this row 0. So this row 0 by the property of Gaussian mechanism is just L square over 2 sigma square. Remember, we're releasing the gradient, and the global sensitivity of the gradient is L, and we're adding noise with the standard deviation sigma, and that's the CDP parameter for that's a CDP parameter for Gaussian mechanism, and then we want to ensure that after the composition we're still getting this 13 times alpha gamma square rho. Okay, so and this constraint will cover this will cover this alpha square. Okay, so then let's try working it out. So what this is saying is that if we choose this sigma appropriately such that this theorem applies, then the total truncated CDP parameter rho is going to be proportional to 13 times gamma square times rho 0 times alpha, right? So this is a total this is a total rho, and we want to make sure that and if we substitute this into above, we know that we got log 1 over delta over 13 gamma square rho 0 times alpha. Yeah, so let's also rewrite this into gamma square and then substitute the expression for rho 0. So this is 2 sigma square L square times alpha. This needs to be smaller than this threshold. This needs to be smaller than log 1 over gamma over 4 times rho 0. Okay, so if we okay, so let me replace this by rho, and then replace this rho 0 by sigma square 2 sigma square over L square, and this is sigma square got flipped to the top, and this is what we this is what we got, and what this is basically saying is a constraint in the following form. What this is saying is L over 2 sigma square needs to be smaller than, if we move this to the other side and flip this to the other side, will have to be smaller than 1 over gamma plus, I guess in this case is what is a factor? It's factor of 4. 1 plus log 1 over delta over this target required rho, right? So this is a kind of a requirement that we need on sigma for us to for the above calculation to hold, for this alpha star parameter to be a valid choice that got covered by these that got covered by this bound when we apply the previous theorem. Okay, so implicitly this constraint is to say that the sigma needs to be sufficiently large, and when sigma is large, then that poses an implicit constraint on T also needs to be large, right? So implicitly this is a constraint. This is constrained on T being large, right? So we'll see how this translates into the constraint for T being large just momentarily. Okay, so we're going to continue these calculations in today's lecture so that we can work out the computational complexity for the noisy stochastic gradient descent, and then I'm going to apply these to deep learning with differential privacy, and then to survey a little bit on other models on deep learning with differential privacy. Okay. Yeah. So same reading from last time. Yeah, there's just one more thing that we need to we need to calculate, right? So just now, like if this constraint is satisfied, then we can apply the truncated CDP bound. So let me maybe using this block to write down what we know about this problem. So there are a bunch of constraints, and 2 of them that we've already worked out. So in the first constraint, this is exactly the same as what I've written down just now, and this is saying that this is saying that this choice of alpha star when we convert CDP to epsilon delta dp needs to be a valid choice over rho. Okay, and rho is our target target CDP parameter, and the second constraint is a relationship between this rho parameter and our choices of T and sigma. So the second choice is from privacy calibration. So we need to choose this T gamma square L square over 2 sigma square. We need to choose this to be rho star. This is coming from the composition over T iteration. Since every iteration gives you gamma square L square over 2 sigma square, then the total P star satisfy it is like this expression from the TCDP amplification theorem. And the third constraint, so notice that the second constraint naturally like gives us like couples this T and rho together. So when we substitute this, this expression and replace this L and sigma square and so on with T and rho parameter, then the constraint 1 becomes like a lower bound on T. And the third constraint is what we are already familiar with from the analysis of the noisy gradient descent, because this is such that we need to achieve the optimal optimal rate of privacy utility trade-off. This is basically saying that the first term of the convergence bound needs to be smaller than the second term. Okay, so we'll work out what the third constraint would precisely like when we work out the convergence bound. Okay, so in the smooth convex case, this is a this expression is a convergence bound that we get. Recall from our discussion just now. So the only difference from the noisy gradient descent is is that like sigma needs to be replaced with something else, right? So this d sigma. So let me cross it out. It needs to be replaced with d sigma square over gamma square. So that's the first term, and the second term, and the second term is n L square over gamma, right? So that's the error. That's a variance that's coming from sampling with probability gamma. So when we have these two terms, then we can choose this eta parameter optimally. So recall in the smoothness case, this eta needs to be larger than it needs to be smaller than 1 over n times beta, and n times beta is a smoothness parameter of the objective function that we are minimizing. So the choice of n really is the max of this and the other eta that tries to minimize everything. So the choice of this is going to be x1 minus over t and d sigma square gamma square plus n L square over gamma. Okay, square root of that. Right, so that's our choice of a constant learning rate, and when we apply these to the bound and then just manipulate the expression a little bit, we can get that the convergence bound can be written in terms of like 3 terms. So the first term will be the convergence of the noiseless gradient descent over t, and the second term will be the term that's coming from this part of the variance. So we'll get I guess d x1 minus x star L square over rho, right? We're also applying the fact that from the constraint true, we know that we know that sigma square over t gamma square. So this is equal to L square over rho 13 over 2, right? So ignoring the constant, and this is the expression that we get when we simply substitute this expression for this is sigma square over t gamma square. So you can see that sigma square over t over gamma square appears exactly here. And the last term is a term that's coming from the variance for sampling, and this is a term that we cannot just get rid of everything that depends on t. So we'll get this the distance from the optimal solution at the initialization. We'll get this n L square. Yeah, and that's it. It doesn't really depend on the dimensionality. So in order to check the constraint, the third constraint, all we have to do is to say that we want to choose t to be sufficiently large such that the first term is smaller than the second term. And we also want to choose this t sufficiently large such that the last term is smaller than the term in the middle, right? So these two gives us two lower bounds on t needs to be satisfied. So from the left hand side, t needs to be larger than n beta square root of rho x1 minus x star over square root of dl, and on the right, this t needs to be larger than n. Yeah, this is slightly simpler because a lot of things cancel out. So we will get n rho over gamma times d. So now the interesting part is that since we're now doing stochastic gradient, in every iteration we don't actually need in every iteration we don't actually need to go over the entire data set, but instead we're only computing gamma times n number of incremental gradient oracles. So if we replace this constraint on the left hand side, instead of lower bounding the t, the number of oracle calls, number of gradient evaluations, and similarly number of gradient evaluations, and then we simply need to multiply gamma times n on both sides, right? So we'll multiply with gamma, and this becomes gamma n squared. We multiply with gamma, which cancels with this gamma. We multiply with n, this becomes n squared. Okay, so that's a total number of gradient oracle calls. But there's like one additional constraint that we haven't addressed, right? So there's this constraint 1, right? So what does constraint 1 look like? So what we can do is to substitute this L squared over sigma from the second constraint inside into the first constraint, and also make an assumption about this rho. So let's say that rho is sufficiently small. Let's say rho is smaller than log 1 over delta. So that's the interesting regime for differential privacy. So in this case, the second term would dominate in this one plus this term, right? So I can replace this 1 I can replace this I can replace this 1 by 2 times two times this expression while still satisfying this constraint. Okay, so if we do that, then we can get that from constraint 1 and 2. These two together gives us t to be larger than square root of rho over log 1 over delta gamma square log 1 over gamma, right? So this is log 1 over gamma, and below this is log 1 over delta. Well, so when t satisfies this condition, the number of gradient calls for the third due to the constraint 1 and constraint 2 needs to be larger than n times square root of rho. Let me just ignore all the logarithmic factors over gamma square. But I also need to multiply with gamma, right? So gamma n times this. So this gamma cancels with this square factor. So it's n square root of rho over gamma. So at the end of the day, like what this analysis is telling us is that the number of incremental gradient oracle needs to be larger by the maximum of all these constraints needs to be satisfied. So it needs to be larger by the maximum of this term, and this term. And what is that? So let's write it down here. So we'll have n squared rho d. So this term like has nothing to do with gamma, right? So we just have to leave it here. But the other two, so one has gamma on the numerator, the other has gamma in the denominator, and we can potentially choose gamma optimally to balance out these two terms. We can choose gamma such that these two terms are the same, so which minimizes sum of the two. Okay, so when we choose gamma optimally, then we can get basically you exclude this gamma and multiply everything together, and then take square root. That gives you the right rate for it. So that gets us to n cubed, and there's a square root of rho times square root of rho gives us rho and beta log 1 over delta over yeah. So let's ignore these. And square root of d L. Okay, and yeah, I think I'm missing this x1 minus x star. Yeah, so when we choose gamma optimally, like this is the computational complexity that we get for noisy stochastic gradient descent. So how do we make sense of this? Basically, when D is say when D is anything that grows with n, when the dimensionality is large, then we can get something that's not as crazy as a quadratic complexity. But the second term is really really proportional to n to the power of 1.5, right? When everything else is a constant. So even though we cannot do anything for the first term, because like choosing gamma doesn't really help us, but if we choose gamma perfectly to be some fractional term that depends on all the other parameters, when we choose a mini batch to be not too large and not too small, and we were able to obtain like we were able to achieve like a much faster computational complexity when the dimensionality is proportional to n, right? So when D is proportional to n, then the first term becomes linear. In the second term, when D is proportional to n, then we can get something like n to the power of n to the power of 1.25 kind of convergence bound. Okay, so all the others, like under the non-smooth convex case and the non-smooth strongly convex case, they are more or less just tedious calculations, that's much similar to what we have previously. So let me very quickly write them down, and so that we can look at we can just compare the so we can just compare the rate. So in this case, well, so the optimal choice of eta, so there are no more constraint on this eta needs to be smaller than 1 over the smoothness parameter, because we don't really have the smoothness parameter now. And the optimal choice of eta is simply one that balances these two. So recall that from the last lecture, we bounded this gradient parameter to be n square L square, right? To be n square L square, because f is a summation of L different loss functions, and each loss function satisfies that it is L Lipschitz, and this is the square of it, so we get n square L square. Then if we choose eta optimally, then we can get that this is smaller than x1 minus x star square n square L square, and then we need to again substitute this with d sigma square over gamma square plus n L square over gamma. So altogether we get d sigma square over gamma square plus n L square over gamma over t, right? So this is a convergence bound when we choose this learning rate eta parameter optimally, and then we can split this into 3 different terms, and all of them have this term in front of them, and then what remains is n gamma t plus d over rho for the one in the middle, plus yeah, I guess this is n over yeah, I guess this is n, this should be n square over gamma t. This is n over t, right? So the last term is n over yeah, sorry, n square over t should be over here. So square over t over gamma. Okay. And then it remains to check all the 3 conditions such that this term is smaller than that, and this term is smaller than that, so that gives you like two expressions, and then the same expression by combining constraint 1 and constraint 2, they are exactly the same as a previous calculation. So ultimately, what we will get is a max of what we get in terms of the number of gradient article, like will be n square root of rho log. So this is from the constraint 1 and 2. And from the constraint constraint above, we get n square rho over d, and then n cube gamma rho over d. Right. So these three terms are by working out these inequalities, and we can get these. And it remains to, I guess, choose gamma to balance out these two terms. Again, this term cannot be compressed in any way by choosing gamma, but we can choose gamma optimally so that the sum of these two are balanced out. So we're getting the smallest possible bound for this expression. And if we do that, so gamma square is equal to, I guess, n to the 4th rho to the 1.5 d, and there are a bunch of log factors, and if we do that, then we end up getting the interesting thing to look at is that when we choose gamma optimally, so we are still getting like n square in this case when we're not assuming smoothness. So it will get a square root of n to the 4th, right? N to the 4th rho to the 1.5 and d, right? So the second term is still like n proportional to n square, right? So comparing to the previous case when we are assuming smoothness, in the more general case when we are only assuming Lipschitzness and convex loss functions, so the improvement is not obvious, right? So even if we have the case when d is depending on n, it's growing with n, like in this term, like we're only knocking off like one factor of n rather than knocking off like two factors as seen over here. Yeah, for the strongly convex case, like things are also just very similar, we've worked it out in the last time that how to. So basically, this bound is obtained when we choose this learning rate to be 2 over t plus 1. Yeah, so when we choose this learning rate, and then when we use a weighted average scheme for the intermediate iterates, we can obtain this 1 over t faster convergence for the strongly convex case. And we're not making any assumption on the smoothness of the loss functions themselves. And what we can do is, again, to replace this with d sigma square over gamma square plus plus n L square over gamma, right? So that's coming from the variance of the stochastic gradient. And once we do that, we can further split this into 3 terms, and the term in the middle gives us the information theoretic limit, and the other 2 terms goes to 0 as t gets larger. So this gives us yeah, I'm ignoring constant. So this is Tuda inequality, say equal up to a universal constant. Sometimes it's a convenient way of writing these scaling argument. So in the middle, we get simply like d L square over lambda rho, and in the last term, we get n L square lambda gamma t. Okay, so both the two terms on both sides goes to 0 at the rate of 1 over t, but we need this t to be sufficiently large so that they are comparable to the term in the middle. And in addition, we have the constraint from amplification by sampling that that says that the total number of oracle calls, the gradient incremental gradient oracle calls, is given by the maximum of these three terms. Gamma. Yeah, all of them have 1 over lambda. Okay, and what we can do is to balance out these two terms, and then that gives us the sampling probability to be I guess n cube rho of d and n to the 4th rho square and yeah, and that's it. And when we choose this, then we get an overall bound of when we choose this, we get an overall bound of just a maximum of 2 terms and n square I guess this is 3 n square sorry, 1.5 rho 0.75 and over square root of d. Right. So again, in the strongly convex case, since we're not making assumption on the smoothness, then we cannot actually get the benefit of it, and the scaling in terms of the number of iterations we need to run this is comparable to the case of the general convex, but to the general convex and Lipschitz case. Yeah, so it's like somewhat surprising, because in the non-private case, the strong convexity is actually giving us a substantial benefit computationally. On the other hand, for the differentially private case, like it's not helping us computationally, but it's helping us information theoretically. So we are getting a better solution that's closer to the optimal solution, but the amount of computations that it takes for us to obtain these solutions is about the same. So they are all proportional to n squared. So quadratic time. So notice that this is already improving over the noisy gradient descent, which is cubic time. With the technique of stochastic gradient descent, we are able to improve the computational complexity by a factor of n. Okay, so yeah, very interesting. A question is that can we actually get sub-quadratic time algorithms for non-smooth convex empirical risk minimization, right? So a lot of this is still like ongoing research that we see papers about like a different optimization algorithm under differential privacy constraints, and they derive some new bounds that outperforms the existing result under some certain regime, and then they write a paper about it. So this is one of these new papers, and they've using the smoothing trick, right? So when they are given a non-smooth optimization problem, so what they can do is to smooth it by modifying the objective function a little bit, and then show that you get an approximate solution. But by using this trick, they are able to improve the computational complexity from this n squared over d plus this n squared over square root of d to this like fractional like crazy expression. But this like should be believable, because we've seen that in the smooth case, when these loss functions are actually smooth, then we are getting n to the power of 2/3 over d to the power of 1/4. So what they got here is that for the non-smooth cases, you do lose something, but what you lose is somewhat more subtle. And what you lose can be described by like replacing this d to the quarter with d to the d to the power of 1/8. Right? So you get slightly worse dimension dependence, but yes, but by modifying the algorithm a little bit, by using the noisy stochastic gradient descent to solve a surrogate problem that approximates the rational problem using a smoothing trick, and then you are able to break this quadratic computational complexity barrier for achieving the information theoretic limit. Okay, and another thing that's presented in this interesting paper is that if we are to so far we've been considering the problem of obtaining the optimal, like empirically optimal solution. So this is just to solve the pure optimization problem without making any assumption about how these data points are obtained. On the other hand, like in machine learning, typically we want to come up with models that generalize, and a natural way of measuring the performance is to compare the solution that you get like on new data points on new data points that you haven't seen before, right? And since for that objective to be true, you don't actually need to overfit your training data and obtain extremely accurate minimizers to your empirical risk, and you can save a little bit of computation over there. So in this alternative and very much related problem of minimizing population risk or future generalization error, then you can end up like massaging these bounds a little bit more and obtain and even knock off factors on the exponent of this n squared over d term, right? So that was also like discussed in this more recent paper. Okay, so as a checkpoint, so I've walked you through the computational analysis of both the noisy gradient descent and noisy stochastic gradient descent. We know that both algorithms, they are able to achieve the information theoretic limit. So noisy gradient descent is better than noisy gradient descent in that sense because it doesn't require privacy amplification by sampling. And as we can see, using privacy amplification by sampling actually requires us to lose a little bit, right? And it also requires us to have additional constraints in the parameter regimes that we can choose from. On the other hand, like if the goal is to obtain the optimal information theoretic limit up to a universal constant, then both algorithms they are sufficient for this task. And it remains to compare the computation. So for this, the NoisySGD is a lot better than the noisy gradient descent in all categories. So we can see that there are improvement in the Lipschitz and smooth cases, and Lipschitz and in particular in the Lipschitz and convex case and Lipschitz and strongly convex case, the improvement is going from n cubed to square root of n, which makes the algorithm substantially more practical. N squared, like it's still some kind of a computational barrier, like for many applications. So often, what we can do is to maybe design like other better algorithms in NoisySGD in the same flavor of the smoothing trick, right? So there it's possible to modify this algorithm so that you can get faster and faster computation. So the open problem is that like for each family of this problem, what is really the optimal computational complexity in terms of the number of incremental gradient oracle calls? So what is required for any algorithm? So far this remains a very intriguing open problem that's nobody were able to solve, right? What we do know is that suppose we in addition make assumption about the generalized linear model, right? And then generalized linear model and smoothness, so we make all the nicest assumptions, then objective perturbation is actually achieving the information theoretic limit. And you do not actually have to do anything incrementally. And for any scalable algorithm that's out there, you can use it to solve your convex program without adding noise to anything, right? So that means that if you believe your first order method or your Newton's method is able to, LBFGS is able to obtain high fidelity solutions to convex programs, the objective perturbation might be your best bet. And is it like if you're restricting yourself to generalized linear model settings. All right, so we'll take a break and we'll resume to talk about differentially private deep learning, and we'll restart the lecture on 2:16.
putting on that's in their accent for that.
They have scheduled.
Oh, okay. Oh.
All right, everybody, it's 2:17. We should resume the lecture. Okay, in the remainder of the lecture, we'll be talking about differentially private deep learning. And the references are primarily Abadi et al., which is now already cited by I think more than 2,000 times. So by the time we start looking at this paper, like it was around 50 times, and now it's gaining a lot of momentum, and it's still going strong. And because it's more or less the only algorithm that works in the differentially private deep learning regime. And then I'm gonna tell you a little bit about the alternative models to differentially private deep learning, which require some additional information. But in return, with this additional information, that you're able to get like more and better privacy utility trade-off. You'll be able to get stronger learning performance at the same privacy budget, but like you need some additional things from that's given to you. All right. So obviously, the noisy stochastic gradient descent algorithm from the privacy perspective, like has no issues at all. Like it can be directly applied to differentially private deep learning, because deep learning are usually learned by first order methods, and then by stochastic gradient descent and ADAM and so on, which requires these stochastic gradient oracles. And now we have a tool that allows us to use a subsampled Gaussian mechanism to privately release this unbiased estimator of the gradients, and then those can be just directly plugging into these existing optimizers. The main challenge, however, is that quite different from convex learning, where we can work out everything analytically. We can restrict our data space and feature space, label space, and we can do the pre-processing to ensure that. And sometimes we can solve constrained optimization problems, such as the parameter space is constrained, which provides us bound of the global sensitivity. In deep learning, we do not actually have that. So we can obviously like use very crude bounds to construct the Lipschitz constant by but those Lipschitz constants will be exponential in the number of layers. And nowadays people are doing hundreds of training deep networks with hundreds of layers. It's just make the theoretical analysis of these Lipschitz constant of individual gradients like very infeasible. Okay, so the key idea from Abadi et al. Is to limit the to limit the contribution of every individual data point when we compute this this mini batch gradient by something called gradient clipping. So the idea is following, instead of updating your parameters with some of this individual gradient plus noise, right? So this is a noisy gradient descent algorithm. But in deep learning, so we do not know the contribution of individuals. So what we can do is to just replace this with something else. So we can replace this with the sum of the gradient. But then I consider two cases. So when the norm of this gradient is larger than some predefined parameter b or L. So when the norm of this gradient is larger than some predefined parameter L, then I'm shrinking this to then I'm shrinking this to a norm being just exactly L. On the other hand, if this gradient is already smaller than L, then I don't do anything about it, right? So what this is saying is that I will multiply this gradient with the minimum of with a minimum of these two possibilities, right? So this is called per example gradient clipping, and if we do this, you can check that this G hat T is a statistical query that satisfies has has a global sensitivity being smaller than L. Right. So when we add or remove any individual data point to this data set, yeah, and then you can only affect the G hat T by a factor of at most L. Right. So that algorithmically enforces the Lipschitz constant of this objective that we're optimizing to be L. But yeah, you can see that there could be all sort of associated problem here. First of all, this gradient G hat T is no longer unbiased, right? It's no longer unbiased, and then the question is that is that like the gradient of some other functions that we're optimizing? It turns out that it also isn't the gradient of some other functions in general, because there doesn't exist such a function where the gradient maps to this normalized version of this per example gradient, right? So it's kind of tricky and how this could work, but this is a practical hack that Abadi et al. Came up with, and it worked like a charm in the differentially private deep learning setting, right? Yeah, I guess so I'm writing the clipped version of differential private gradient descent. For the stochastic gradient descent, you need to sample first and then replace this summation with a sum over all I in the sampled mini batch. Okay, like they also introduced several other tricks to make differentially private training of neural networks more practical, including using smaller and narrower neural network. So quite different from the common wisdom of using large and over-parameterized neural network to maximize the performance. For differential privacy to work in deep learning, so sometimes you have to stick to narrower and smaller neural network and to more aggressively reduce the dimensionality. And they also proposed to use a private principal component analysis to pre-process the input data, so that your input data will have a much smaller dimension to begin with, so that the first layer of the neural network parameter is not going to just get crazily large. Right. So with all these tricks, and then like this method will work. And I'm showing this slide to tell you like how like straightforward it is to implement this algorithm in AutoDP, so that you can do the privacy accounting using state-of-the-art tools. So after finishing the first homework, like you should already be somewhat familiar with this. In AutoDP, like we represent each mechanism with a class, and it comes with its own parameter of interest, and this probability is just this gamma parameter that we've talked about in the NoisySGD, and this sigma is a noise multiplier, and this sigma is the same as this L over yeah, I guess sigma over L. Right, so the actual amount of noise that you add is this sigma parameter that you enter here, multiply with the global L2 sensitivity, and then you should specify how many iterations you're running this algorithm, and then it's using the extended packages from that's available in AutoDP by instantiating a subsample transformer, and the transformer will take one mechanism and convert it into another mechanism, and this is subsample amplification by sampling, and then you say that what is the mechanism that I'm amplifying, so I'm instantiate a Gaussian mechanism with this noise multiplier parameter, and then I specify what the probability is, and the subsample Gaussian mechanism is simply applying this transformer and use this to transform this mechanism with these additional parameters that we set. Okay, so this gives me the subsample Gaussian mechanism. The next thing is to just go to the transformer zoo and find another animal called composition. And in this case, we can instantiate this compose callable object, and the compose is also something that can transform like one mechanism or a list of mechanisms into another. So what we can basically do is that that we are composing. We are just composing the subsample Gaussian mechanism with itself. And how many times are we composing? We're composing this by n iterations, and that gives me the overall instance of this NoisySGD mechanism. right? But this is not a class, and we want a class definition. So later we can adjust this probability sigma and n ether. What we will do is just to take out the Renyi differential privacy from this object, and then propagate to the rest of this this class that we are initializing. So that's how NoisySGD mechanism is implemented from scratch. Is basically take all the already available building blocks and just manipulate them according to how we understand this mechanism works. So notice that this is completely independent to the actual implementation of the algorithm, because this is like a simple tool that helps us to say know what is the epsilon parameter given delta, what is the delta parameter given epsilon, what is the Renyi DP parameter given this different alphas, and then it's doing this mechanism specific analysis like on your behalf. And you can also use this to do privacy calibration to see like suppose I want epsilon delta DP in the end with these two numbers, epsilon equals to 2.0, delta equals to 10 to the power of -6. And what is a corresponding sigma parameter that I need to choose when I fix n ether and prop, and there are some ways that you can do that in the tutorials. Okay, so once you do that, and instead of working with the asymptotic approximation and choosing all the parameters according to our asymptotic bound, now you can just use the Renyi differential privacy or privacy profile to plot these figures and combine that with your actual implementation of these algorithms that add noise to every stochastic gradient. So these three figures were reported from this Abadi et al. Paper. They are on the most basic deep learning example on the MNIST digit recognition dataset. So the typical baseline for this in the non-private world is like 99%, right? So we were able to get 99% on MNIST for I think 3-4 decades now. But in the private differentially private training, so we can see that when they set epsilon to be 0.5 or 2.0 or somewhat a larger epsilon equals to 8.0, then you get different level of privacy utility trade-off. So as you optimize your network using Noisy's stochastic gradient descent, and after composing the subsample Gaussian mechanism for every iteration or every hundreds of iterations, then you can use it to output your epsilon parameter as a function of delta, or delta parameter as a function of epsilon. So when you enter epsilon to be 0.5, then it gives you delta. So delta, for instance, over here, this is 0.7 to the power of minus 5. Right, and on the other hand, on the vertical axis on the other end, you get the you get the I guess this black line is a privacy curve, and this red line and this dotted blue line, they are the accuracy curve. So you can see that both your empirical error and your error on the testing data set gets smaller and smaller as you train with more iterations. So as you increase this epsilon parameter, so apparently you get better and better performance. So when you get to epsilon equals to 8, you can get this accuracy up to say 97%. So if you look at the fine print, they projected the 700 something dimensional original MNIST problem into just 60 dimension using differentially private principal component analysis, and they use like a relatively smaller like feed-forward neural network with just 1,000 hidden units and maybe just 3 layers. But these represent some of the very earliest experiments on differentially private training for deep learning, right? So every one of you could have done this. But it's one of the things that the simplicity is one of the reasons this paper took off. Like then they tried out the same model and with some careful tuning on just a slightly more non-trivial baseline called CIFAR10. So CIFAR10 is also kind of a classification data set with just 10 very blurry category of images of the same size of MNIST. So they apply their method on it, and the state of the art back then in 2016 on CIFAR 10 is also something around like 95-96% accuracy. But we can see that even if we set epsilon to be 8, then differentially private learning algorithms on CIFAR 10, you are still seeing a huge gap between what you are able to get with what is privately with what is achievable, like without privacy constraints, right? So you can see that. So these are the same data set with similar sizes and similar baseline performances on the non-private model, but when we introduce differential privacy to this, like the accuracy took hit at completely different levels, right? So this is like must be suggesting something more fundamental than this. So what are so special about these data sets? What are some of the properties that we can generalize and understand under what circumstances differentially private deep learning works, and what under what circumstances it doesn't work too well, right? So yeah, that kind of understanding is starting to pick up now, and we'll actually be talking about some of these insight in the last part of the last chapter of the lecture on data-dependent differentially private algorithm design. So what we now know is that when a classification problem has a larger margin, right? So when your classifier is able to classify different objects with high confidence, and then privacy is relatively easier. And MNIST, so even though it sits in the really high dimensional space, people believe that with some standard tweaking of these features, and without either end-to-end learned feature or the handcrafted feature, and then using a linear classifier to that will give you like a relatively big margin. On the other hand, for CIFAR 10, it is a completely different story. The data set is a lot noisier, and you cannot hope to get like nearly perfect accuracy. And for those data points that you get right, then you are not that confident, which means that adding or removing individual data points may have a bigger impact in the classification accuracy on the CIFAR 10 data set. Yeah, so people are still working on this by introducing all kinds of tricks to improve the performance on CIFAR 10 and other computer vision tasks. So I wanted to also talk about this clipped per example gradient a little bit more, because it's something that's somewhat broken from the optimization perspective. So I'll give a very simple example to illustrate why this is broken. So let's consider just two data points and the linear losses. So let's say and both of them are in one dimension. So we have x1 and x2 in say on the real line, and in fact, let's say that it is just between -1 and 1. Let's say that the loss function L1 theta, and theta I guess is also from -1 to 1. Okay, L1 theta is x1 theta, and L2 theta is just a linear function of L2 x2 inner product with theta, right? Since these are just scalars, so this is x1 multiplied theta, x2 multiplied with theta. Okay, so now let's choose this x1, x2 to be specific value. We can choose x1 to be let's say that we can choose x1 to be 1.0, and x2 to be say -0.5, and then let's say that we will clip the gradient at say 0.5. Then if we evaluate the gradient, say the gradient is independent to theta, right? So if we evaluate the derivative L1 theta, so this gives me 1.0, which is pointing towards the right hand side. And when we evaluate the gradient of that, it gets -0.5, it is pointing towards the other direction. And now they all got shrinked and clipped to 0.5, right? So moving towards the gradient direction would mean that you are you're just moving moving nowhere, and the sum of the clipped gradient is going to be 0 for any input parameter theta. And so your optimization algorithm, the gradient descent algorithm, will just stay there. And the only thing that's different is that you're adding noise to it, right? So it becomes just a random walk on that -1 and 1, and it drifts here and there, and it has nothing to do with the data at all, right? So when you construct other examples, say with x1, x2, x3, you can come up with cases when when the clipped gradient is actually pointing towards the alternative direction. So let's say that if x1 is equal to 1, I guess x2 is equal to 0.3, and x3 is equal to 0.3. Let's say we clip at minus 0.3, minus 0.3. If we clip at 0.5, and what would you get? The actual gradient should be the actual gradient of the full objective function of the sum of this I from 1 to 3, like should be 1 minus 0.3 minus 0.3 equals to 0.4. But suppose we sum up the clipped gradient. So we will get like 0.5 minus 0.3 minus 0.3 equals to minus 0.1. Right, so the direction of the gradient can be the negative direction of the actual direction that you should be moving. Right, so because of this, so it is somewhat difficult to understand how this, for example, clipped gradient is actually doing. So even though it is doing really well, and the understanding is still not there except for very special cases. So for the generalized linear model, so recall that generalized linear model are the kind of model where this L theta x y. So this can be rewritten as some link function, some univariate link function. I guess that depends on y of x transpose theta. So it depends on the linear function of the feature. So this is a function of theta, but it also depends on a linear function. So when this when this link function f is convex, then we say that this is a convex generalized linear model. So the gradient clipping has the generalized linear model has a nice property that the gradient of L is by the chain rule is proportional to x, right? So this is equal to x f y prime x transpose theta. And thanks to this property, clipping of the gradient is not going to change the direction of the gradient, right? So it's only going to modify its magnitude, but not the direction of the gradient. And for this reason, you can try working out that it was shown in the Shuang and et al. in a recent paper that in a recent paper that there actually exists another link function, right? For any such f that is convex, there exists another link function that captures this gradient, captures this clipping of the gradient in generalized linear model. And it essentially has a effect of robustification of your original loss function, right? So if your original loss function goes to infinity a lot quicker, say it is a quadratic function, then what this is doing is to make it a Huber function, right? So more generally, this is called Huberization, or the robustification of the loss function. And basically the only thing you need to show is that at this piecewise at this transition point of this piecewise region, and the derivative is actually continuous and continuously differentiable, or at least Lipschitz, and that makes this overall function also convex. And but the original link function might not be Lipschitz, but after clipping, this link function becomes Lipschitz. Okay, so this offers an interesting interpretation of the gradient clipping in the convex learning world, which says that you're basically just optimizing like a slightly different objective function. Okay, so I guess the same design idea can be done for deep learning, but unfortunately, like the same interpretation is no longer true when this f of y is non-convex. Okay, so that's all I wanted to say about the noisy gradient descent applying to deep learning. So I've shown you some empirical results. I've also shown you some new theoretical understanding on the gradient clipping and some of its limitations. And these limitations have motivated people to consider whether there are other ways that we can do differentially private deep learning that does not require us to modify the optimization algorithm, because any such modification to the optimization algorithm would be somewhat ad hoc, and we do not understand its failure mode. And it sometimes works in practice, but in other times it could fail quite drastically. So the knowledge transfer model is an alternative to the standard differentially private deep learning model that assumes the knowledge of an available public data set. And this public data set can be unlabeled. So let's say that we have a bunch of public data set that's available to us. So I'll give you an example. Say in the hospital setting, when the hospital is conducting like the clinical study, some patients they want their data to be protected and they want differential privacy. Other patients might, out of goodwill and out of the endorsement of the kind of social welfare that conducting such clinical study can bring to the society, that they may agree that their data is used in the clear, right? So this is one of the settings where you have a mix of private data and data that you can actually use while protecting only security but not privacy of the individuals. Another example can be, say, a tech company is testing their new software, and there are some beta testers that wanted to use a new feature early, and in these agreements, so sometimes like in order to use this product early and have a preview of this, you will have to agree to less stringent privacy terms. So those are another cases where you can have different level of privacy protection for different groups of individuals in your data set. Under these examples, and sometimes like the features themselves are just not, for unlabeled data, the features themselves are just not sensitive at all. It basically describes the property of a general population. And in those cases, you have a huge amount of available public data that are unlabeled. And it might be the labels themselves that needs to be protected. So in all these situations, we have a smallish public data set and a large private data set. And how do we make use of a small public data set to learn, say, possibly deep learning models without understanding anything about these deep learning models, right? So if the non-private deep learning model works, then I want to use it as a black box here. So here's the idea. So you take your private data and you split it into disjoint partitions. You split it into disjoint partitions. It's important that they're disjoint, such that any individual data point can be within any can be inside any one of these only one of these data partitions. And then for each data partition, you train a deep learning model. You train your favorite deep learning model and call them teachers. So you get teacher 1 to teacher n. Okay, and then you take your you enumerate over your data points, that your unlabeled data point in the public data set, and call them queries. And then these queries, you use this unlabeled data and pass them to this bag of teachers, and each of one of these teachers will give you a prediction, right? And then let's ask these teachers to vote. Do you think this is a cat or a dog? And each teacher will give you an opinion, and you add up their histogram. You add up their votes into a histogram, and then you privately release this histogram. Or you can use report noisy max or exponential mechanism to privately release the argmax of the label. So either way, you aggregate the teachers using noise adding or more basic differential private mechanism, and that creates this y hat, right? This y hat 1 is coupled with the public data x1, then y hat 2 is coupled with the public data x2, and the y hat m is coupled with the public data xm. And this becomes labeled data sets that's entirely in the public. And then you can just feed this into your student learner. This could be a deep neural network. And then you use this to create a model. And this model, since by the principle of post-processing, like this model is going to be differentially private if this Y1 to Ym are differentially private. Okay, so I hope the idea is clear, right? So there are M copies of this. So you need to compose over, say, M Gaussian mechanism or M exponential mechanism or report noisy max for this aggregation step. So that's private aggregation. So how does like this private aggregation of teacher example look like from AutoDP? Like it's even simpler. So I argue it's even simpler than the NoisySGD. Because like from a privacy perspective, it's just a composition of Gaussian mechanisms. And we know that for the composition of Gaussian mechanism using our using our privacy profiles and this trade-off function interpretation, as well as this dominating pair. And it's just a matter of adding up of privacy loss random variables. And the privacy loss random variables, since each one of them is Gaussian, then the summation of them is also like a Gaussian. So we had this theorem from a lecture before that says that the composition of adaptive composition of K Gaussian mechanisms, they are equivalent to a Gaussian mechanism with a modified privacy parameter, with a modified like sigma parameter. So this is what this AutoDP is implementing. So you basically can instantiate by inheriting this basic Gaussian mechanism class from the mesh mechanism zoo and then call it Pate. And then you can figure out like if it is binary classification, then you only have to release one coordinate and the sensitivity is 1. And suppose you want to release a multi-class classification problem, then the histogram you release will have global sensitivity of square root of 2. So I'll ask you guys to maybe work this out later in the last homework. But yeah, it should be quite straightforward to see why this is the case. By adding or removing individuals affects only one of the teachers, right? Therefore, at most one of the teachers, and therefore, like when the teacher changes his or her opinion on the output, then all you have to add is just all you can change is 2 coordinates of this voting histogram. And besides that, like since this allows for adaptive composition, there are all other kinds of tricks that we can use to improve Pate on the outside without worrying about how differential privacy is obtained. So in particular, we can use something called noisy screening to check which are the data points that are worthy of labeling and which are not. We can also use release only the argmax, and sometimes that has a privacy amplification effect rather than releasing the full voting score, right? Because it's a post-processing of a voting score, and sometimes when you have high margin and you can show that it actually incurred a much smaller amount of privacy, you can use the sparse vector technique, and yeah, this is also something that we've learned, together with something called distance to instability, which is one mechanism that we'll cover in the last couple of lectures. And moreover, like there are this like data point selection that comes with theoretical guarantee called active learning from the machine learning literature, right? So we can simply plug in any active learning framework into this problem and use them to select the data points to label. And in this way, the smaller number of data points that we annotate, we privately release, that we query our private data for, and the smaller amount of privacy budget that we'll have to use. And the more accurate that we can release these synthetic labels. Right, so all of these tricks are working. And a slight modification of Pate is to make it the so-called private KNN, which uses a very similar idea. So the difference is that instead of having teachers being neural networks, so now the teachers are just nearest neighbors, right? So you find your K nearest neighbors and then try to privately release their voting score. So think about adding or removing any individual from the entire data set can only affect one of your neighbors, right? So one of your k nearest neighbor will be swapped with someone else who moved even closer to you comparing to the k plus first neighbor, and that's bounded sensitivity. And you can privately release the private k nearest neighbors score, and then keep iteratively updating the feature extractor on how you and what is a metric, what is a distance function you use to compute this k nearest neighbor, right? So Yu-Xiang and us and our collaborators like work this out and then demonstrate that this actually leads to substantially better performance comparing to Pate and NoisySGD. Right. So another thing about KNN is that you can now actually leverage the privacy amplification by sampling, because you can sample a subset before you compute the KNN. Right. So that is not achievable for Pate, and that makes the algorithm more adaptive and more flexible. And since this is just a composition of subsampled Gaussian, then we can leverage the same NoisySGD class and then instantiate how we can do privacy accounting for private KNN. There's a noisy screening step, but the noisy screening is simply a post-processing of Gaussian mechanism. And so this is really the compose and Gaussian times 2. And then before Gaussian, you amplify that by subsample. Right, so this is really what it is, and what we enter here for this sigma will account for both Gaussians, like for the noisy screening step and also for the noise adding step. Okay, so I'm out of time, so I'm gonna just skip through this this slides. You guys can take a closer look at it. We compare to NoisySGD and to Pate, and you can see that at highly reasonable privacy parameters, we can now like get much improved performance. Say on MNIST, we're now getting like 98.8 comparing to 99.2 like non-private accuracy. And we also have like some theoretical study on Pate that in a similar flavor to the kind of tedious calculations that we had like earlier for NoisySGD. For this new learning paradigm, then we can come up with their statistical guarantee and to characterize this privacy utility trade-off. And in short, like these theoretical results is SVT style methods works, active learning also works, and if we make like assumptions on how the labels generated, satisfying something called the Tsibakov noise condition, which helps active learning to improve the sample complexity, that also helps the private learning even when we are not doing active learning. All right, I'm gonna stop here, and in the next lecture, I really have to start talking about the going beyond the worst case and talk about data adaptive differential private algorithm design. All right, I'll see you guys on Wednesday, and sorry for running a little bit over.